Today we got a video that's going to talk about one of the most beautiful equations in mathematics, an instance of Euler's identity or Euler's equation. It relates imaginary numbers and oscillating sine and cosine functions, and we're going to use it to solve a Griffith's problem. This is one of the starred Griffith's problems. It's very important. It is in the free particle section, and I think it's a fantastic problem because it actually arises in many other parts of the Griffith's book. So yeah, we're gonna do this problem. We're gonna do it off the rip, no solution manual, no help, no nothing. I'm just gonna zoom through this. These videos may be long because I'm just gonna discuss what I think. If I'm on a test and I have this problem in front of me, I'm literally just gonna go off the dome and write something. If you're in a scenario like this and you don't know how to answer a question, you wanna write down as much shit as you possibly can. Basically write a whole page if you can, if it's like a short answer. Spew out all the information you can think about related to this problem and give the grader as much content to work with. Anything you write is going to be helpful. Let's get going. Let's read the problem. Over here, this is problem 2.17. Show that a e to the power of ikx plus b e to the power of minus ikx and c cosine kx plus d sine kx are equivalent ways of writing the same function of x, and determine the constants c and d in terms of constants a and b, and vice versa. Comment: in quantum mechanics, when v is equal to 0, the exponentials represent traveling waves and are most convenient in discussing the free particle, whereas sines and cosines correspond to standing waves, which arise naturally in the case of the infinite square well. Awesome. How do we even solve this problem? I'm going to start off by writing what we know. What do we know? We know that e to the ikx plus b e to the minus ikx, and the other thing is equivalent. So equivalency literally means equal sign. So I'm going to do equal sign and write down c cosine kx. Normally there should be like brackets over here. I'm going to put these brackets. Plus d sine kx brackets. All right, we've created our first equation. What's our goal? We have to find a proportional to c and d, and we have to find b proportional to c and d, and vice versa. C proportional to a and b, d proportional to a and b. What does this mean, proportionality? It just means find an equation that has a, c, d all in one, and find another equation that has b, c, d all in one. Preferably a equals something c, d, and b equals something with c and d in it. So here's our equation. This is going to be the main slamming point. So this is something you have to pick out from the problem. I'm literally using nothing except the words equivalent over here. All right, now what can we do? Well, what I was thinking of doing when reading this problem, something that I thought of incorporating, is Euler's identity. Mr. Euler, Euler's, let's do identity. I don't know if it's actually an identity or an equation or a theorem or something like this, but I know that e to the ix is equal to cosine of x plus I sine of x. And I also know that if we multiply something here, kx, then we get cosine kx plus I sine kx. Maybe another useful thing to do is figure out what it happens if there's a minus sign over here. So I don't know exactly what happens, but I do know that you can bring the minus sign into the equation. So let's just slap it onto the k. So I will have minus kx over here plus I sine minus kx over here. I'm literally working with what I know over here. Now, how can we manipulate this equation over here? Let's use some blue. I'm going to just manipulate this equation a little further and see what happens. I know that, well, let's determine what cosine of minus x equals. I know that cosine looks like this. So cosine starts at 1, it goes down, does this, and it goes over here and does that. All right. And while we're at it, let's, I guess, also do sine. So this is cosine of x. Let's do sine of x over here. I know sine starts at 1 and goes up, or it starts at 0 and goes up like this. Boom. So looking at this, you can see that cosine looks like a mirror, all right? It does the same thing here as it does over here. This is what you call an even function. While sine does the opposite. This looks like it is completely reversed, right? So this is called an odd function. What can we say about even and odd functions? Well, take a look at this. Let's say this over here is x. Then the same thing over here, the same distance on this side and on this side, you would have minus x, the same thing. And you can see cosine is equal to the same thing. So what that's telling me is cosine minus x is equal to cosine of x. Maybe I can erase this, just write this a bit more clean. Cosine of x. So this is a property of an even function. It is the same regardless if you change the input by slamming on a minus sign. But let's take a look at the sign. If we take a look right here at the apex, whatever this x is, we can take a look at the same distance. So this distance over here on the negative x-axis, this distance over here, we have this, which looks like it's exactly the same, but just minus. So what this is telling me is sine of minus x is equal to minus sine of x. If this was a little bit confusing, no stress. Take a look at some plots of these functions, try to convince yourself. Or if you want, literally grab a calculator, throw in sine of minus 1, throw in sine of plus 1, throw in sine of minus 0.2, sine of 0.2. Test it out with an example case. But I know that this is true by just working through it. So now what I can see is that this equation over here, basically what happens is this minus sign from the cosine disappears. It can just literally change into a regular cosine. But for the sine, this minus gets pulled out in front of the sign. So this over here will change to a minus, and I can erase this minus here. Nice. So now we have two cool equations that we can work with. I'm going to circle these in red. Amazing. So this is what kind of tool I think will be helpful for me. So now we have this blue equation over here and this red equation over here. And you know what? I think this is enough to solve the problem. So I'm going to literally just grab this, but I'm going to grab it like this. Hold up. Am I able to do this? I'm trying to just grab only these things. Nice. Copy this. Again, remember the goal. We're trying to find a and whatever in terms of the other ones. Paste this right here, and let's shrink this down a bit so that we can use it later. Okay, this is what we've developed. This is just what I pulled out of my ass. Let's see what we can do here, guys. Let's see what we can do. What do we do? You know what? Let's just apply the equations. I'm not a big fan of these exponents. They're a little bit scary, so I'm just going to work with the cosines and sines. So what that means is I see there's an e to the ikx here. E to the ikx here with the Euler identity. I could just replace that whole thing with this, multiply that by a. There's an e to the minus ikx, e to the minus ikx. There's a b. I'll just multiply by b here, replace that whole thing with this. Amazing. Let's test that out. We'll write it here. So a, I'm going to actually just distribute the a already. So we have a cosine, and you know what? I'm not going to write these brackets because writing the brackets is going to be annoying. Ia sine kx. That's the first term. Then we have b plus b. Then we have cosine kx. And then here we have a minus ib sine kx. Can we do anything here? I guess we can combine things. So you know what? I'm going to do equals left-hand side. This is the left-hand side of the equation. I'm just going to work with this and then combine it with the right-hand side. So right here is the right-hand side. What I've just done is manipulate the left-hand side. All right. Now I can see there is a cosine over here and another cosine, and the cosines are the same because the arguments are the same. The only thing is the factor out front, but I can combine these cosines, factor out the cosine, and then there's an a plus b there. I see the same thing with the signs. There's a sign over here and a sign over here. They're the same sign because the arguments are the same. And the only thing that's different is there's a plus I over here and there's a minus IB over here. So what I'm going to do is combine cosine kx. The factors in front of this are the A plus the B. Then I'll do plus sine kx. What we have here, whoops, is factors that look like IA. Should we pull out an I as well? No, I think we should keep the I's inside. I'm just kind of looking in the future what's going to happen. I think we should keep the I inside because there is an I common to both of these. Right, so I can pull the I, have the I out here, but I don't think I want to do that. I think I want to keep the I in here. That looks like it's going to be useful for me. And then there's an IB. This equals the left-hand side. What have we done here? Here's the cosine. I have pulled out the cosine. One of these terms stays over here. Here's another cosine. I've pulled this cosine out over here because it's common. And then there's an addition because this is a positive cosine, this is a positive cosine. Then I've combined the sine, pulled the sine out from here as well. There's an IA over here, IA, and a minus IB, and I add both those two together. I think now we're ready to go into the left-hand side. I'm just going to write the left-hand side. This is C times cosine kx plus D sine kx. This is equal to the right-hand side. What can we see here, guys? Well, these two things are equal. Over here we have a cosine kx. Over here we have a cosine kx. The factor that is being multiplied by that cosine here is a plus b, and here we have a c. So we literally got our answer. C is equal to a plus b. I'm going to circle that or box that in red because that is our first answer. That looks crazy. How are we doing on time? 12 minutes? Bro, my videos are always very long, so I'm going to try to do it quick here. Here we have a sine, and I'm literally just equating these because the right-hand side equals the left-hand side, and here we have a sine, and here we have a sine. It is a summation of a cosine and a sine, a summation of a cosine and a sine. And there's factors. There's a c factor here, and there's another unknown factor. We can call this entire thing a c, and then the equality is identical. I hope you guys see what I'm saying here. What we have in the sine is a d, and then this thing over here. So we determined our other value. D is equal to IA minus IB. Nice. Okay, and this is our answer, but the problem is we weren't just asked for that. Determine constants C and D in terms of A and B. Did we do that? Yes. Here we have constants C and D. They're determined and they're in terms of A and B. And there's some I's in here too. Why does the D have an I? Because the D is in front of the sine. I think we're going to get too philosophical if we start talking about this. We're going to do a lecture video on Euler in the future. Sorry for slamming that bottle. But we also have to do vice versa. So we have to determine, maybe let's write this in a little cute orange. A equals something and B equals something in terms of C and D. How do we do this? Well, we have two equations here. This is tough, guys. This is tough. Can we isolate for something? Because I don't know. If we go back to this equation here, or these equations, like, what can I do here? I don't know if I see any other pathway. Aha! I think I do see a pathway. Nah, I don't actually see a path. Okay. What I did here was, here is our original equation. I pulled this out straight from the problem. Here is an adaptation of Euler's identity. What I did was use this thing inside here, right, and convert these into sines and cosines, and then I isolated these things. Or no, I combined these things and I isolated for these ones. Is there a way for me to, instead of replacing this, isolate for cosine and plug this cosine into here? And then isolate for a sine and plug this sine over here? I don't know how I feel about that. I think that's going to be too much work. I guess you could do that. It's math is going to work out at the end of the day. But what I'm thinking is, here we have two simple equations. Is there a way for me to just isolate for A? I think there is. Guys, I think there is. Here's what I'm going to do. Here's what I'm going to try to do. I'm going to start with one equation. Let's say this is equation 1, this is equation 2. Let's start with equation 1. I'm going to isolate for A. A is equal to C minus B. That's okay. Let's go to equation 2. Let me go to this white color now. So equation 2 is D is equal to IA plus... Oh, I got it. We replace the I, A. So we have I. Inside the I, we have inside the A, we have a C minus B, right? Then we have minus IB. Now what can we do? We can replace the C from equation 1, this equation over here. So if you guys saw what I did, I isolated for this A by moving this B over here. So the B was moved here. Now I have an equation just for A. Over here, I take this equation and I see an A in here and I have an A here. So I just replace this A here. That gives me this term right here. Everything else stays the same. Now what I see is a C over here. And again, my goal is to find A and B in terms of C and D, right? Here we have D. Wait a second. Nah, bro, it's not gonna work. I don't know. Here's what I'm gonna do. I'm just take this C, plug it in here, because that eliminates the C. There's no more C anymore. So I just have D and an equation of A and B. That's gonna do nothing. I'm gonna get like 1 equals 1 or something like this. But you know what? Let's try it out. So what I have here is D is equal to I. Then we have A plus B minus B minus IB. Brother, this is ass. I'm literally back to the same boats. Okay. Alright, we're tripping here. This ain't good. This ain't good. How do we do it vice versa? You know what, bro? I think I'm gonna have to literally just start from here. And yeah, we're gonna do it. We're gonna do it. We're gonna do it the other way. I thought this video was gonna be nice and smooth, nice and easy, but 17 minutes. We're gonna zoom through and try to finish this before 30 minutes. Okay, let's isolate for cosine. I don't like how this is looking. Okay, I'm gonna take this equation here, isolate for cosine. Cosine kx is equal to e to the I kx minus I sine kx. And yeah, that's it, no? No, it's not feeling good. Alright, I'm going to take the equation and substitute in this cosine. So we have AE IKX plus BE minus IKX. This is the full equation. Here we have a C cosine, but the C cosine gets replaced into a C e to the IKX minus IC. I like putting the I in front, sine KX. So this is cosine, right? Now we have to also replace the D sine. How do we replace the D sine? So there's this equation here. Let's do another one for sine. Sine kx is equal to e to the I kx, but there's an I here, but 1 over I is minus I in the numerator. And then we have minus cosine kx. This might actually work out pretty good, I'll be real. This might actually work out pretty good. Okay, I see it coming through. I see it coming through. I see it coming through a little bit here. But there's an I in the denominator. I in the denominator becomes minus I in the numerator. This becomes a plus. Vibing. Then here we have minus, okay, plus D. So here we have minus ID e to the IKX, alright? And then here we have plus ID cosine kx. Maybe I was getting hyped too early. Okay, here's what I did, guys. Here's what I did. This stuff stays the same, right? This stuff stays the same left-hand side. Boom. This thing over here was replaced from cosine kx. Notice the c carries over to both of these terms. I use this first equation Euler identity here. I had a cosine over here isolated for this cosine. So the cosine becomes this, right? We have e to the I kx here, e to the I kx here. Move this I sign here. This becomes minus I sine kx. Boom. Replace that here. Here's e to the I kx, e to the I kx, minus I sine kx, minus I sine kx. There's two c's because the c's come from this cosine substitution. Ballin'. Now, I use the same equation here. This is where I was kind of tripping here. I'm like, okay, I used this equation. I used each of these. I used this one and this one in the first go, and everything went smoothly, super simple, super easy. Now I was like, okay, I used this one to isolate for cosine over here. Should I use this one to isolate for sine? Or should I use this one to isolate for sine? I decided to go with this one. So I isolate for sine. How I do this is just move this cosine here. This becomes minus cosine kx here, right? E to the I kx, e to the I kx minus cosine. But there's an I here, which I want to get rid of because I'm trying to plug in sine over here. So I divide I on both sides. This I gets canceled. Here I have 1 over I in the denominator. But 1 over I, you can multiply by I in the numerator, denominator. This is just multiplying by 1. There's an I now in the numerator. I times I equals minus 1. This minus 1 can go in the numerator. So basically, I in the denominator is equal to minus I in the numerator. This is where this minus I is coming from because I divided this I over here again. Now we have a minus cosine here because we moved this cosine on the other side. But the I in the denominator goes up and it makes this minus a plus. Okay, now I substitute this sign from here, here. So we have a minus e to the I kx minus e to the I kx. There's an I here, I forgot about that. Then there's a d here, boom. Then there's another d here and the I cosine kx, boom. All right. What I was getting excited about here is here we have a cosine and a sine. Now we can use the second equation perhaps, but it's not looking clean because we have an I in front of the sine and the cosine. If we could have used the second equation to get rid of this, then we will have an entire equation in terms of these, and that made me feel good, but I think we're not there yet. So okay, here we have the left hand side is this equals right hand side, and the right hand side equals what can we combine? We literally can't combine anything, bro. We can't combine anything. Okay, time to use the other equation again. Here's what I'm gonna do. Here's this second equation, okay? I want to get rid of this. Oh, here it is, boys. Here it is. Okay, watch this. I'm going to isolate for this I sine kx because there's an I sine kx over here that I can plug this shit into, right? This means this cosine, oh wait, maybe I got excited a little bit too early. This cosine goes here, but the cosine doesn't have an I in it, brother. All right, we're going to move through by just isolating this minus, let me write this in pink, minus I sine kx is equal to e to the minus I kx minus cosine kx. Let's plug this into here. Plug this, actually, it's a little weird. Plug this into here. And that means the right hand side is equal to c e to the I kx. This is where the minus comes in, huh? So we have plus c e to the minus I kx. Oh, this is looking okay, actually. Oh, this is looking good. Because the C's are all on one side, huh? I mean, they're always on one side. 24 minutes, bro. This video is going to be 4 hours. Let's keep bulldozing, though. So it's plus here, plus C e to the I kx. And then we have a minus c cosine kx. I still don't feel great about this. I feel like I'm just gonna be making substitutions forever. I_kx plus id cosine kx. Okay, let's see where we left off. This stuff here stays the same. All right, stays the same right here. What I did was substitute this, except this c gets pulled out and gets multiplied onto both of these, and that looks good. Here there's a plus, here there's a minus. And then we are left with this over here. Can we combine anything? No, we can't, but check this out. Here we have a c, e to the ix, c e to the minus ix. This very, very similar to this, because this looks like c is equal to a plus b. Am I really just getting down to the same thing as before, bro? Let me think here. Let me think. I don't even know what I'm thinking about. Like, I guess I'm just taking a break a bit. Let's see what we're doing here. I don't know if this is it. Scratch it. We're gonna go back to these two equations because this makes me feel a bit better. Like, I think I'm just gonna substitute for eternity on the other method. But I think I incorporated these a little bit strangely. So I'm gonna try incorporating them in a different manner. Check out what we got here. Can we eliminate or somehow do something here? Oh man. Maybe. Watch this. Yo. Okay. D is equal to I. Factor out the I. We have A minus B. Right? Divide both sides by I. Right? Divide by I. Divide by I. What do we get here? I's cancel on this side. I in the denominator becomes minus I in the numerator of this. Now we have A minus B. Okay. Now peep this. C is equal to A plus B. Now check this out, guys. Check this out. If we do minus ID equals A minus B plus C equals A plus B, check out what we're doing here. If we add these two, I'm basically just adding these two equations together. Add column wise. Add this, equal sign remains, add this. So minus B plus B is equal to 0. A plus A is equal to 2A plus 0. Equal sign stays. Then we have C minus ID. And we did it, boys. Oh my god, brother. Oh, this makes me feel good. A equals c minus id over 2. And this looks good to me. This looks good to me. There's no errors here. How do we check if this is true? And if we add the equations together, then we can just as easily subtract the equations to get the other one, huh? I think that sounds good. Subtract. So if we have minus b minus b, first of all, let's do the first one. Minus id minus c is equal to a minus a is 0, minus b minus 2b. Now we have b, move it to the other side so it becomes positive. Move both of these to the other side so it becomes c plus id over 2. Oh, this looks so beautiful, man. Oh my god. We got this. Let me copy down my other 2. Duplicate. Bring this down here. Is this the answer, bro? How do I even check if this is the answer? I think this is the answer, guys. Okay, so if you're feeling good, 30 minutes. Thank you guys for watching. 30 minutes is not bad for a problem like this, right? Off the rip, too. No help needed. I hope this is correct. We're going to check solutions up here in the side. If it's not correct, the video is probably going to be like another 30 minutes longer. But we got 4 equations now, and what we could do is plug them into each other to see if it works out. So let's plug in a and b into c. So here we have, this is going to be the check in green. C is equal to a, which is c minus id over 2, plus b, which is c plus id over 2. We should get some unity here. We should get c equals c or something like this. So what can we do here? C is equal to, everything combines because the denominator is the same, so we have c minus id plus c plus id over 2. Yeah, this is looking good to me. So there's a minus id plus id. Then what we have here is c plus c, 2c over 2. The 2's cancel, and we get c is equal to c, which is good. Honestly, we're chilling, bro. This is the answer. Let me pull up the problem too. And yeah, this is how you do some math, guys. Thank you guys for watching. If you want to see more problems like this, let me know which problems you want. I'm doing the ones that are important. As you can see, there's a star on this one, so Griffith thinks it's important. I think it's important because this application here is used in many problems. The infinite square well has a section where the potential is 0. So solutions are going to look like, in the infinite square well, we have sines and cosines because you can use boundary conditions very nicely with sines and cosines. But you can also write it in terms of exponentials, imaginary exponentials, because it's identical. We just show that it's identical. It just has different coefficients. But in the free particle, the potential is 0 everywhere. There, you don't like to use sines and cosines. You more prefer to use exponentials because they represent traveling waves better. That's what the guy is saying right here in the problem. Then we have the finite square well, which also has a potential equal to 0 outside the well, right? The finite square well is 0 everywhere except this little box where it's like minus some certain potential. Outside the well, there's traveling wave solutions. Inside the well, there's some trapped states, bound states or whatever. And those I think you can write as sines and cosines. But outside the well, I think it is traveling waves, if I'm not mistaken. It actually depends. It depends on your energy too. So this is a travel back to my other video where I showed a bit of a difference between bound states and scattering states. This is actually very important, so I'm going to do another video on it. Bound states, scattering states is completely different. They yield different solutions. So scattering states normally yield the traveling wave solutions. Bound states, normally you use sines and cosines. I'm not going to yap too much about this. If you enjoy this problem, leave a like, follow, share this video with your friends, with your family. I'm sure your grandmother and grandfather would enjoy watching this video. And yeah, appreciate it, guys. Peace out.